Hello everyone, myself Dr. Suman Saha, Assistant Professor, Department of Chemical Engineering, India Institute of Technology. And today I am going to discuss about the topic uh, under Chemical Engineering Thermodynamics, that is development of Maxwell's equations using essential properties. Now, before going to analyze the essential properties, so we have to know about the classification of energies, and energy can be classified by two types. One is the macroscopic energy and second one is the microscopic view of energy. In the macroscopic view of energy, all those are related to the outer reference will be known as the macroscopic view of energy. For an example, kinetic energy, potential energy, magnetic energy, all are related with the outer reference of the system. But in the microscopic view of energy, those energies are basically related with the internal arrangement or molecular behavior, molecular structure, structural identifications. All those are involved in the internal uh, in microscopic view of energies. And for an example, like translation energy, rotational energy, vibrational energy, spin energy, all are example of microscopic view of energy. And if we add or sum all these microscopic view of energy, then we can get the sensible energy of the system of one molecule. And now if one system is involved with a number of molecules, then into sensible energy will give you the internal energy of the system. And this internal energy is related with the first law of thermodynamics also, and these relations among and the heat, work and total energy that will be reflected on the first law of thermodynamics, which is denoted as energy can be neither created nor destroyed during a process. It can only change the form. That is energy in minus energy out will be equal to delta energy or change in energy of the system. In terms of heat and work, delta Q minus delta W will be equals to delta E. But if system is not affected by outer reference like gravity, capillary, position, motion, electricity, magnetism, then total energy will be converted into the internal energy of the system du. And if we replace the du in terms of the dE, then equation number 2 will be delta Q minus delta W will be delta U. That is equation number 4. And the second law of thermodynamics often leads to expressions that involve inequalities. An irreversible, that is actual heat engine, for example, is less efficient than a reversible one operating between the same two thermal energy reservoirs, and by which the process inequality will come as its cyclic integral of delta Q by delta T, the thermal degradation of heat, that will be less than equal to 0. And this inequality is valid for all cycles, reversible or irreversible, that is delta S or ds, change in entropy, is equal to delta Q by T in internally reversible condition, which is denoted as equation number 6. And this can be rearranged as equation number 6 can be rearranged as del dq reversible is equal to tdns, that is equation number 7. Now The first law of thermodynamics for a closed system of n moles of a substance will be dnu equals to del dq reversible plus dw reversible for as equation number 8, and work done dw is equals to minus pdv equation number 9. If we put the value of dw over the equation number 8, then it will be dW for n number of n moles of molecules, that is dW equals to minus PDNV. And for second law, from the second law of thermodynamics, there exists a property called entropy, which for systems at internal equilibrium is an intrinsic property, that is dst equals to ds total. T stands for the total entropy, equals to dq reversible by t, and dq reversible is equal to tdns. Now from equation number 8, 10 and 12, dnu equals to tdns minus pdnv, where u, s, v are molar values of the internal energy, entropy and volume. All of the primitive thermodynamic properties P, V, T, S, U are included in this equation. That's why this is known as the fundamental property relation, fundamental property equation. And equation 13 is known as fundamental property relation, connecting this property for closed PVT system. And from enthalpy relation, H is equal to U plus PV, which is equation number 14. Multiplication of equation number 14 by n, we can get for n number of molecules, followed by differentiation, yields the general expression as dnh equals to dnu plus pdnv plus nvdp. This is nothing but the multiplication of uh, n for the number of molecules present in the system, and after that the differentiation of equation number 14, which gives you the equation number 15. Now from equation number 13 and 15, we can get another one fundamental property relation, that is dnh equals to tdns plus nvdp, equation number 16, where H, S, V are molar values of internal enthalpy, entropy and volume. Now other two relations are based on two new combination properties. Number one is the Helmholtz function, that is A equals to U minus Ts, and question number 17, and another one is the Gibbs function G, that is equals to U plus PV minus Ts, and U plus PV is the enthalpy, so then it will be reduced to H minus Ts. This is equation number 18. And now one by one we will solve the differentiation problem, that is differentiating equation number 17 according to n number of moles. We get dna equals to minus nsdt plus minus pdnv. How we can get that, is that explanation we are just getting over here. Like we know Na equals to nu plus minus dns. Okay, so dna equals to dnu minus tdns minus ns dt. Now from equation number 13, which is dnu equals to tdns minus pdv, so we can easily replace dnu minus tds as the minus pdv. Then we can write as dna equals to minus ns dt minus ns dt minus pdnv, which is denoted as equation number 19. Now from equation number 18, from Gibbs function after derivation, it will be dng equals to minus ns dt plus nv dp. And equation number 20, and its the explanation. Now dnh equals to dng equals to dnh minus tdns minus ns dt. From equation number 16, we have dNH equals to TDNS plus NVDP. So dNH minus TDNS will be give you the NVDP. So in the replacement of dNH minus TDNS, we can easily write plus NVDP. So minus NSDT plus NVDP. Minus NSDT plus NVDP, proof of equation number 20, which is another one important property, fundamental property. So equivalent fundamental property relations. So these equations that relates the partial derivatives of properties PVTs of a simple compressible system of each other are called the Maxwell relations. Now, for fundamental equations, we have dnu equals to tdns minus pdnv, dnh equals to tdns plus nvdp, dna equals to minus nsdt minus pdnv, and dng equals to minus nsdt plus nvdp. Now, a careful examination of these four Gibbs relations reveals that they are the form of dz equals to mdx plus ndy. Okay, so where we can correlate with the following expression: del m by del y at constant x is equal to del n by del x at constant y. Let m is equal to del z by del y at constant x and n is equal to del z by del x at constant y. Taking the partial derivative of m with respect to y and of n with respect to x yields del m by del y at constant x is equal to del 2z by del x del y, and del n by x del x at constant y will be equals to del 2z by del x del y. Due to the order of differentiation is immaterial for properties since they are continuous point functions and have exact differentials, therefore the two relations above are identical, and del m by del y at constant x will be equals to del n by del x at constant y. These two are identical. And this is an important relation for partial derivatives, and it is used to calculate the test about the Maxwell equation with the help of the exact or inexact differential equation. Now, if we take the equation number 13 for n equals to 1, then it will be d equals to TdS minus PdV. Consider the exact differential of internal energy U at constant volume V. It becomes del U by del S at constant V equals to T, del U by del S at constant V, that is equals to T, and PdV, that will be equals to 0. Suppose this is equation number A. Differentiating the above with respect to V at constant S, then it will be del 2 U by del V del S equals to del T by del V at constant S. This is equation number B. Now again, at constant entropy, this will be del U by del V at constant S equals to minus P. Equation number C. And differentiating with respect to S, at constant V, then it will be del 2 U by del V del S equals to minus del P by del S at constant V. Now from equation B and equation D, del T by del Vs is equal to minus del P by del S V. Equation number 22. This is the first of the four Maxwell's equation. Now from remaining three equations, using equations 16, 19 and 20 are obtained in a similar way. Del T by del Ps equals to del V by del Sp. Equation 23. Del S by del Vt equals to del P by del Tv. Equation 24. Del V by del T P equals to minus del S by del Pt. Equation 25. These are called Maxwell relations, like equation 22 to equation 25. And these Maxwell equations are extremely valuable in thermodynamics because they provide a measurement of the change in entropy which cannot be measured directly. Now another one example of Maxwell equation is like where Maxwell equation can be applicable, that is Clapeyron equation. That Clapeyron equation is one such relation, and it enables us to determine the enthalpy change associated with a phase change, such as the enthalpy of vaporization from knowledge of P, V and T data alone. Consider the third Maxwell equation, del S by del Vt equals to del P by del Tv, and during a phase change process the pressure pressure is the saturation pressure, which depends on the temperature only and is independent of the specific volume. That's why Psat is the function of temperature, saturated temperature, and partial derivative that will be converted into the saturation point. And the total derivative of del P by del T saturated is the slope of the saturation curve on a PT diagram at a specified saturation state. This slope is independent of the specific volume and thus it can be treated as a constant during the integration of the third Maxwell relation between two saturation states at the same temperature. And from isothermal liquid vapor phase change process, for example, the integration yields del S by del Vt equals to del P by del Tv. From here, we can get Sg minus Sf equals to del P by del T saturated Vg minus Vf, del P by del T saturated minus equals to Sfg by Vfg, and during this process uh, pressure is also remains constant, and from the enthalpy balance if we reduce the pressure, then this integration will be coming as Sfg equals to Hfg by T as equation number 28, and substitute this equation result in equation 27 that dP by T dt saturated is equals to Sfg by Vfg, and dP by T saturated is equals to Hfg by Tvg, equation number 29, or dP by dt saturated is equals to delta H by d delta V, which is called the Clapeyron equation. Thank you.